Okay, thank you everyone for inviting us to have this say user meeting or seminar, and we would like to uh, give some lectures about the AFM application in nanomechanics. And thank you, Dr. Shi and Dr. Gordon, and invite us, and we are old friends now. So it's the third time we have this kind of user meeting in Hong Kong. And the first year we talk something about the basic principles of the AFMs, and last year we did something about the so-called nanoelectrics. So this year we want to give another topic. It's about the mechanics. And as usual, the broker, they always starting from to talking about how good the broker is. So everyone knows. So I would jump this topic and just give this slides to you. And this slides just help our customers to know how to reach broker. And once you need something wrong with your hardware, something wrong with the softwares, and sometimes you need support from us, you can always find us using. You can call us or send emails to us, or use the say WeChat or other things. So that's the page I would like to share with you. And then so we jump this the blah blah blah, and go directly to our science. So we are talking about the nanomechanics. So in our topic, we prefer to give you or give our users to better to use these machines, not just to make this kind of lecture as manuals or something like that. So I prefer to starting with the science first about this thing. So again, we were talking about this thing again, starting with the main purpose we are using the AFM. So the atomic force microscope. So the name of this machine is the microscope. So once you read this word, you know you want to watch something. So the basically application of the AFM is a microscope. So it's doing the imaging. So once you're doing the imaging, you just want to take a picture and then take pictures. The main purpose of the AFM images is to tell you the 3D topography of your sample, right? And the only advantage of this technique is doing this kind of imaging at the nanometer scale. That's the basic the AFM. And we know starting from the beginning, the AFM is just like, as my professor said, the AFM is the same as lab, it's blind. Basically, your probe did not know what it's scanning. So you just control your probe to scan the surface, and this scan the surface tells you what it looks like, but it cannot tell you are scanning at gold, you are scanning at carbon, you are scanning at some fantastic 2D materials. No, it cannot tell you that. It can only tell you the morphology. So once we know the morphologies, we all want to get more information to say what's the chemical components, what's the physical properties of the surface. So we want to know the properties, not just the topography. Although the topography, the images is the most fundamental things of the AFM, absolutely. But we want something more. So, for example, when we're talking about the image for, say, some researchers, they are doing the alloys. So they are doing alloys, they would form different phases. Something is mainly with iron. Some other parts it has tin or something like that. So we want to do this kind of alloy, for example, this alloy research, we want to know the distributions of different components. So this topic is imaging. You want to know different components, how it distributes in these materials. This topic is we're talking about imaging. And for this kind of topic, we only need to know where is what. That's the only questions. We know this main component here is iron. The other part, the main is tin. That's it. That's good enough for us. And then, besides this kind of imaging, we want to know more about the property itself. So we are doing our researchers invented some novel 2D materials. Nobody did that. They want to know what's the thermal conductivity of this 2D material. We want to know what's the electric conductivity of the material. We want to know what's the modulus of these materials. We want to know the property. But this time, the property is at nanometer scale. Nobody did that before. So for this kind of purpose, we want to do some quantitative thing. We want to get some number. Basically, we want to get some number. And this number, we want it to be measured at the nanometer scale. So that's basically the two main purpose we want to get with these machines. First, the main application is we use this as a microscope. So it tells us how the distribution of different components inside our sample. So we use AFM as imaging scales. The only thing is the basic fundamental AFM is we just capture the morphologies, the topography. But now we may want to use the property to distinguish different components. So basically, we still get an imaging, a mapping. And we know this part is iron, this part is tin, that's enough. We don't need to know the property itself. The another application is we want to measure the property. And this time, we want our measurement of the property is at nanometer scales. So that's the two applications of our AFMs. We want to do it. So for this part, the things may be quite easy because we only need to use an AFM. It can distinguish different components. For example, we have iron, we have tin. Everybody knows tin is softer than iron. So once you get alloy, and you want to know, okay, what's the distribution of tin among this alloy, and then you have an idea. If I can get a so-called hardness or modulus mapping of my materials. And then from this mapping, I can get some part is hard, some part is soft. And then I can know here should be my iron, here should be my tin. I don't need to get the I don't need to get the correct number of the modulus or hardness of this tin or iron. I don't need to. I just need this difference to get the mapping. That's it. So this kind of applications, we don't require any accuracy. We don't need any accuracy in numbers, in quantitative. We just need to make it different. That's it. But for this, that's another story, right? We need to get the numbers. For example, we invent the 2D materials. Nobody did that before. And I place my 2D materials on the, say, gold 111 surface. And then I capture an image, and I can see a clearly triangle morphologies. That's it. I know this one is my 2D materials, period. I don't need the so-called the modulus mapping or hard disk mapping. No, I don't need that. I know this is my 2D materials absolutely. My purpose now is I want to get the hard disk or the modulus, all these 2D materials at the nanometer scales. That's it. I don't need you to tell me it is 2D materials. I know. I need to know the number. Okay, that's the another a little bit different purpose of compared to the images. So the imaging, we are talking about imaging. We want something the resolution, but for the properties, we want something accuracy. Okay, that's the two different purpose of our research. So if your research is focused on the get the imaging, get the mapping, get the distributions, we don't need to waste our time to get the quantitative results. But if we want to get the quantitative results correctly, we don't need to bother about the resolution. We can use some quite blunt probes. We can use some notch probes. It sacrifices the resolution, but we get the quantitative results. So that's the two different purposes. Okay, so we know that, and then we can continue our research. So, for example, if your purpose to get a mapping, you don't need to worry about the accuracy, right? But nowadays, the research, the research is different from before. Some of our critics, some of our reviews, when we submit a paper, our reviewer always said, okay, you get a good image. Please tell me the modulus of your sample. But your purpose is just to get the image. I don't need to worry about the number. But time difference. Nowadays, our reviewers will always ask something like that. Once you get this, it will ask you, okay, could you give me a more sharp or clear images of your sample? Our reviewers always want us to obtain two purposes. But for us, we need to know at the beginning. Okay, so we know the difference, and then we can continue. So this week, our topic is about the mechanical properties. So when we're talking about this topic, I would split into two parts. So the first, we need to talking about how to use AFM to distinguish the property, the mechanical properties, and then we can get some imaging, and then we can go to the topic how to get the accurate number. Okay, so we can start. So we are talking about the AFM tool in the mechanics. So the mechanics, the mechanical properties or the mechanics. Basically, it just used to distinguish how hard or how soft a material it is. And for this kind of the mechanics or the property study, our researchers, they have a fixed pattern to study a certain property. Once I give you a device or a material or a sample, I want you to study its mechanics. What we did first, we want to give it a stimulus, right? We want to give it a stimulus. So basically the English word, we have an action. And once you put an action on this sample, on these materials, it will give you some feedback. The feedback is the reaction. So that's basically how people to study the materials, how to study the property over new sample. When you're talking about how you want to measure the conductivity, what you did, you apply a voltage on it, and then you measure the reaction of the voltage. What's that? That's the current, right? And from the current and the voltage, you using the Ohm's law to get the resistance. For our mechanics, what we did, we apply a force on our materials. And from under this force, we would observe, we would expect our sample would do something, will do some reactions to our force. And this reactions, I already know, is the deformation. From the relationship of deformation and the force, we get the property of our sample. And these properties, we call it stiffness, we call it hardness, blah, blah, blah. And we call these properties a mechanical property. Right? We call it, and that's the way how to study the mechanical properties. We need to give it something. We need to give it an action, a force. Okay, so, and then at the beginning, we want to make our topic to be more clear, because under people's the experience, they know the deformation, it has two parts, it has two categories. The first category, we call it elastic deformation. The elastic, this word is, I'm sorry, I don't know the origin of this word, but when I go to school, I read this word, I don't know what's its meaning. And then some researchers, my teacher told me about the elastic. It's when you apply this force, it will give you a deformation. When you release the force, the deformation will be gone. So this kind of elastic deformation is kind of reversible. So and as such, for this kind of deformation, we call it elastic deformation, and its property, we call it elasticity. And then another category is plastic deformation. The plastic deformation is different with the elastic, is that once you release the force, the deformation will be there. So it will not return, it will not be gone, it will always be there. So we call it plastic, okay? For this kind of two deformations, absolutely we will have two different properties. For the elastic deformation, we call it elasticity. And for the plastic, of course, it's the plasticity. And then we will fix our topic today or this week mainly about the elastic deformation. We want to study the elasticities at the beginning. So we define our definition. The next is to get the property or get the relationship between our action and the reaction. So our action now is force. The reaction is the elastic deformation. When we're studying a new properties, our basic or the easiest the relationship between two things is what? Is our linear relationship, right? So we want to establish an equation, something like that. This force equals to something times the deformation. Basically, that's our basic the relationship we want to study, the simplest one, right? And this one, we know it in high school, the famous Hooke's law. That's the Hooke's law, right? And when we study in high school, the Hooke's law is used to study spring. Once we apply a force, the spring will have the spring will extend, and the length change, we call it delta L. We call it delta L, and the Hooke's law is something like this. And we call this K we call it this K as the spring constant. That's the Hooke's law. So it's basically just to describe the property of our elastic deformation. We apply a force, it gives us an elastic deformation, and then we will get this relationship. And this A in the Hooke's law, we call it the spring constant. And then basically we expand this Hooke's law into the whole elastic deformation. We call this stiffness. That, as such, we establish our basic the relationship between our force and the elastic deformation. And then when we study the mechanical properties, the main topic is to measure the stiffness. Okay, so basically it's the same as the Hooke's law we study in high school. We have the so-called the serial connection, and we have the parallel connection, right? We have two springs. If we connected it to, if we connect the two springs in this serial form, we will say, okay, what's the spring constant change of this one? So for the serial, the spring constant K should be defined as, I'm sorry. Yeah, it's here. For the serial connection, the total K should be something like this, right? And for the parallel connection, the total K will be the sum of each component. And this kind of relationship can be applied to our stiffness. So when we have when we have two devices, we combine them in the serial connection, the total stiffness will be reduced. But if we combine them in the parallel fashion, the total stiffness will increase, right? It's just the same as the Hooke's law we study for the springs. Okay, and then we want to expand we want to expand more about the stiffness. Okay, so when we're talking about stiffness, we are talking about a real thing, a real device. We say in this world. I have this red pen, I have this black pen, I have this blue pen. Basically, you all know they are made from the same properties. They are made of same materials. So basically, I have one pen, two pen, three pen. I combine them together. It should give us the same material, right? But from the stiffness, we can know if we make this pen thicker, it will be more stiffer. If we make it longer, it will be less stiffer, right? That's the property of our stiffness. So basically, when we're talking about stiffness, we should consider two things. First, of course, what's the material of my sample, of my device? If I'm using a plastic or iron, different materials should give me different stiffness. But on another side, is we need to consider the shape. If it's thicker, it will be more stiffer. So when we do research, the things may be different. For example, you invite a new 2D materials, you get this kind of triangle. And on another day, your lab mate make a small one. But it is still the same materials. And if you want to measure the stiffness, the stiffness of these 2D materials, they are different. But in your heart, you want to know, okay, I want to know some properties of the material itself, regardless its shape. Okay, so basically the stiffness includes both material and the shape. We want to focus on the material itself. Basically, we want to get rid of the shape. So how we should do this kind of get rid of the shape. So basically, that's the main purpose in the next step. So we know the shape. From the parallel and the serial connections, we know the shape. It includes two different formation. The first is the serial connection. The longer, the softer. So the serial means the stiffness is proportional to this one. And we know the parallel. The parallel means the thicker, the stiffer. So this kind of parallel relationship told us the stiffness should be proportional to its area. So it contains the contribution of area and length. So my topic now is when I want to get the material contribution, I need to get rid of the shape. So the shape contributions has two components. One is length, one is the area. So my task now is to get rid of the length and area. So the next step is straightforward. So I starting from the Hooke's law, the force equals to the stiffness times the deformation. And we know we're talking about the elastic deformation, so I use the deformation for short. Okay, and then this stiffness should have three components. One, it has something to do with the material itself. Second is the two shape contributors. The first is proportional, I'm sorry, it's proportional to this one, so I put it here. The next is proportional to the area, so I put it here. The whole thing together is the stiffness, right? So the material components is our holy grail. I just need to get rid of another two. Okay, so I just make my holy grail here, and this one I read it. Its length here is the deformation. Deformation is the change of length. So I combine them together. And for this area, please go to another side. So I get rid of the area and put it here. Put it here. So this one is the force per area. So it's just tells us the at a certain area what the force looks like. Okay, it's something like our pressure, right? Something like our pressure. So then I look at this Hooke's law. It has nothing to do with the length. It has nothing to do with the area. The only things left, it should be the material contribution. So at this step, I can stop. I can stop. So I gave it another name of this coefficient. We call it modulus. We call it modulus. And then also about its unit. The deformation of over length, the unit should be 1. The force per area, the unit should be Pascal. So the unit of our modulus, it should be the Pascal, right? And then for this kind of equation, we also call it Hooke's law. We also call it Hooke's law. And then deformation over length, force per area, we also give it another name. This one we call it stress. And for this one, deformation per length, we call it strain. So finally, we get rid of shape from our stiffness. We get the strain equals to modulus times strain. So basically, both stiffness and the modulus tells us the properties, the mechanical properties of our thing. The stiffness is we're talking about a real thing, a real device. But the modulus, we get rid of its shape. We get the property of the material itself. So in our study, we use the modulus in more wide applications. Okay, that's the easiest way for this kind of deformation. Okay. This kind of definition is quite easy, but in the real mechanical worlds, it is always something different, right? So we want our, we want our research to be continuous. So basically in mathematics or in the physics, how we want to make our research to be continuous, the way is we use the calculus, right? We use the calculus. So basically our force, our deformation, our area, we should make it infinite small. So basically the strain should be defined as the dF over dA. The stress, we should make it something as the dx as the x, something like that, right? Something like that. We need to make it continuous. We need to make it small. So we invite the calculus here. So the first change. The second thing in our physics is we have direction. We have directions. So basically, when we're talking about the force, the length, the area, it's just some numbers. But in the real physics world, we always need to consider the directions. So basically, everything should be vector. Okay, when we're talking about the vectors, the game is different. So we're starting with the stress and the strain. I leave it here for your reference. The stress, we use the Greek we use the Greek letter sigma, and its definition on this slide is force per area. And the strain, we use epsilon. It's the deformation over length. Okay, so the first we need to introduce calculus here, and the second we need to consider the direction. So we live in a 3D world. We live in a three-dimensional world. So we're starting with the 3D things. So the force as a vector, it should have three components. It's a 3D world, so it has three components: fx, fy, and fz. Right? And of course, you can using the matrix way to write it down. For example, you have many ways to write it down. So you can using the you can write it down as the fx times this one, fy times j, and the fz times k, right? Or you can use the matrix way, fx, fy, fz times ijk, right? That's the basic, the matrix. So make it simple. I just write it down fx, fy, fz. For the length, it should also be a vector. So it also has three components: x, y, and z. For the area, it also has directions. So it has three components: ax, ay, az. So for the areas, the directional area, you remember in your mathematics class, you get a surrounding of the area and using the I think I remember right, is the right-hand node to define its direction, right? So area, it also has the directions. It has AX, AY, AZ. Okay, then we are starting with the strain. I'm sorry, stress. Stress is defined as the dF over dA. Okay, so I introduce the differential here. So I make it dfx, dfy, dfz, and dx, dy, dz, dax, day, daz. So for the stress, it should be a df over da. So what it should look like? Right, it make me some difficult to consider it. So I would make it something easier. So I write it down in this way. dF should equals to stress times dA. Of course, this one is not correct in mathematics, right? We cannot do the calculus in this way, but it does not harm in the physics to understand how the stress looks like. So I make it down in this fashion. Okay. So our mathematical genius know that this one is not correct in mathematics, but in physics, no harm to do it. So for the dF, we have so I will write down here. Okay. So go here. Okay, so dF, we know it has three components, dfx, dfy, dfz. So I can write it down, dfx, dfy, dfz. Okay, and the center part is my stress. Another thing is about the dA. Okay, I write it down, dax, day, daz. So in this fashion, we can tell what the stress looks like. It should be a certain matrix. It at least should be looks something like that. 3 times 3 matrix. So it at least it should have line components. So the first one is the dfx over dax. The next one, I write it simple, x over y. Okay, you understand it's the dfx day. Okay, but make it simple, I write it down as the xy. The third one should be xz. Okay, the fourth one should be fy over ax. The next one should be yy. Next one is yz. The third line, it should be the zx, should be the zy and the zz. Okay, so this one should have a form of this kind of matrix. And in the physics, we know its name is tensor. So basically, when we're talking about the stress, in the physics, it's a certain thing, it's something. And this something, when we use the mathematical way to describe it, the mathematical formation, we call it a tensor. And it has many ways to express this tensor. A certain way we're using the matrix. Okay, so the matrix is just a form of the tensor, right? So the stress is a tensor. So basically, you have the stress tensor. Of course, we have the strain. I'm sorry, strain is red. strain is dxx dy. I'm sorry. It's the deformation over length. Or basically, the deformation is the change of length. So it's the d delta L. So it should be also a tensor. It should also be a tensor. And how it looks like. Write down, right? The strain is also a tensor. So the stress is a tensor, strain is a tensor. The stress, it has 9 components. The strain, it has 9 components. So our next question is, what about the modulus? It absolutely should be a tensor. How many components it has? 9 times 9 equals to 81. So to completely describe a modulus, you need to have 81 components. So that's a lemma, right? So to fully describe, I need 81 numbers to get the modulus done. How can I reduce my task? So basically, for this kind of thing, we need to use symmetry, right? The symmetry, our world is symmetric. This kind of bottle is this kind of column shape, and for this one, it's also column shapes, right? So we need to use the symmetry to help us to reduce this kind of numbers. So I'm sorry. The easiest way or the most perfect symmetry in this 3D world is sphere, right? It's sphere. If our materials is sphere symmetric, it should make our, say, it should make this kind of modulus or other properties expression should be much simple. Okay, so when we are consider this kind of sphere, the sphere. Okay, the spheres means it's the same in all directions. So if it's the same in all directions, we have a kind of physical world, we call it isotropics, right? We call it isotropic. So if our material is isotropic, it means all the directions is the same. I do not need to distinguish the x, y, z because they are the same. So for the sphere, when I'm talking about the stress is a force on a certain area, but this kind of my material is sphere symmetric, so all directions should be the same, right? So the stress, it will be reduced to be the same of all 9 components, right? So the sigma xx, sigma xy, I can write it down. The whole matrix, they are the same. So I just write it down as the sigma. For the strain, it's the same. All components should reduce to a single number. That's the epsilon. So the strain reduced to 1 component. I mean, it still has 9 components, but all 9 components, they are the same. The strain, it has 9 components, but they are the same. So what about my modulus? The strain, just 1 number. Stress is 1 number. Strain is 1 number. So my modulus, it should be also reduced to 1 number. Right? But once we finish this kind of isotropic study, we may realize it's has some different things. So here, for example, I have a sphere here. No matter which direction you compress on this sphere, it should give you a same elastic deformation. That's the isotropic. So no matter what the directions I apply force, I should get the same elastic modulus numbers. So the modulus number should be only 1. But for this kind of sphere, once we apply a force on it, it's no longer a sphere, right? This bottle, this column, you apply force in this way or in this way, that's the same, right? But once I compress in this way, this part and the another part facing you, they are different now, right? I compress this way, so this direction is different from the another directions. So for the sphere is the same. I apply a force in this directions, and it gave me a deformation to be something like this. And after this deformation, it is not isotropic anymore. It divided into 2 parts. The part is the direction along my force, and another part is the perpendicular to my force. So for example, I apply force at z directions. So after the force, z and x, y, they are not equal anymore. So of course, my isotropic material, my sphere symmetric materials, yes, they are the same in all directions. But when I study the mechanical force, the mechanical properties of it, once I apply a force, it will be divided into 2 parts. The one is the force directions, the another one is the force perpendicular directions, right? So some guy, oh, you know this name, this French guy, Poisson, he realized this kind of issue. So he defined another number to distinguish the difference of the z and xy. So for example, I use the way of my slides. For example, I apply force on the z. So the epsilon z should be equals to dz over z. And then I have the epsilon x and the epsilon y. Since it's isotropic, so x and y, they are still the same. But these 2 numbers, they don't need to be the same. They don't need to be the simple. Actually, I don't have any relationship to define this 2 string components, right? So I have to leave it there to use another coefficient to describe what's the difference here. So this kind of coefficient, the Poisson gave it a name, is Poisson's ratio. So this Poisson's ratios, in his definition, of course, we know when we apply a force on the z directions, so the epsilon z should be negative, right? It should reduce, the deformation is negative, but it will expand in the x, y directions. So the Poisson's, he defined his ratios in such way. So it means the Poisson ratio should always be positive, right? You compress this way, it should it should expand in y and z. Of course, nowadays we invent some magic materials. They are lactive Poisson ratio. You compress it, it will compress in y and z. But that's the nowadays physics. But in his days, in Poisson's days, the 19th century, the Poisson ratio is positive. Okay, so the Poisson ratio is positive. So since the x and the y is the same, so I compress in the z, this deformation should expand in equally to y and z. I'm sorry, equally to x and y. So the Poisson ratio in his definition should have a maximum, it's 0.5, because y and x and y are the same. So the Poisson ratio is less than 0.5 and larger than 0. That's the classic definition for the Poisson ratio. So the Poisson ratio, so how we understand the Poisson ratios? For example, we have what's our material of the Poisson ratio 0.5? That's the same cannot be compressed in volume. So basically, this kind of bottle, its Poisson ratio should be should reach 0.5. You compress in this direction, it should always expand in another directions. And what about the Poisson ratio 0? What's the materials? What's your daily life's materials? It's using such kind of Poisson ratios. It means you expand, you apply force in one direction, it will not expand in another two directions. So this one is used widely for our daily in our kitchen. When you drink wines, it has a piston, right? It has a piston to just to seal your wine bottle, and this piston is to I remember it's using a wood. I'm sorry, I forgot the English. The name is 橡木. Yeah, you probably know that word. I forgot its word. This kind of wood, its Poisson ratio is 0. Means when you open this kind of piston to unseal your wine bottle, you just drill it, right? You drill it, you apply force in the z directions, and you won't want this kind of piston to expand in the x, y, so it will not break your bottle. So its Poisson ratio is 0. You drill in z directions, but it will not expand in x and y. So that's the Poisson ratio 0 materials. So that's the Poisson ratio. So after that, we finally can conclude our elastic modulus for isotropic materials. For homogeneous isotropic material, we should have two numbers to describe its fully elastic properties. First, we have this number. We have this modulus number. It gives us how hard this material it is. If it is larger, means this material is harder, right? Simple. But we also need another property, we call it the Poisson ratio. And this Poisson ratio is used to describe what's the relationship between force direction and the force perpendicular direction. So we have the modulus and the Poisson ratio, two numbers. It gives us a fully description of the elasticity. or in our tensor ways, we can say the elasticity tensor, it should have 81 components. For isotropic materials, the 21 components will be reduced to only 2. One, we call it modulus number. Another one, we call it Poisson ratio. Okay, so after that, we can have the fully description of our materials. Okay, so but for other crystal materials, I'm sorry, we need to get our symmetry back. So for salt, for sugar, they have different crystallized structures. So we need to do different things for that. And of course, you know that theory, that's the group theory, right? So we do not want our this lecture to be fully on this physics. So we make it simple here. We stop at the isotropic materials. Okay, so for isotropic materials, easy. We only need 2 numbers. One is modulus, another one is the Poisson ratio. I'm sorry, Poisson ratio is not sigma. It should be mu, right? Should be mu. Okay. So after this, we can continue. So finally, we establish our way to describe the mechanical properties. So we're starting with the Hooke's law, and then we introduce the definition of the stiffness. The stiffness is just the same of the spring constant here. Okay, so starting with there, we get the stiffness definition. For the stiffness, it contains 2 components. One is material, one is shape. We hate the shape. We want to get our holy grail. So we get rid of the shape. We get the sigma equals to the modulus times strain. Strain is epsilon. So the modulus in the mathematics, we use capitalize E. We use the capital E to describe the modulus. That's our equation. So for both equation, we call it Hooke's law. But for this one, we know, okay, the strain, the stress should be tensor. It's 3 times 3, it has 9 components. And for elastic modulus, it should have 81 components. And then for isotropic, these 81 components will be reduced to 2 numbers. The first, we call it modulus. The second, we call it Poisson ratio. So that's the isotropic description of the modulus. And it's the same as the of your of your mathematics. So for example, on this plane, I have a certain point here. And how I want to describe the position of my points. What should I do? I need to establish a scale, right? So the easiest way is this kind of perpendicular scale. I have the x, I have the y. So to get its location, I just need 2 numbers. The location, x and y, right? But this kind of perpendicular scale is not just it's not the only scale I have, right? I have another scale. I can use, I'm sorry. I have polarized scale. I can know its amplitude. I'm sorry, amplitude. I know its angle. So using the amplitude and the angle, I can also describe its location, right? This polarized scale and the perpendicular scale, they are actually the same, just a different way to describe this thing. So this thing in the algebra, that's just the transformation of different scales. So for the modulus, for the elasticity, we know it's just a certain tensor. And for this kind of tensor, we can also use a certain very complex matrix to describe it. Or in a more accurate word, we should call it a linearized space, right? And for this space, for the isotropic space, it has two bases. It has two bases. One way to describe these two bases is we use the modulus and the Poisson ratio. Of course, you can do another scale transformation to another different basis, right? That's the game in algebra, right? Of course, in the physics, we also play the same words. We play the same game. So we have the modulus. Usually, this kind of modulus, we use the name Young's modulus. I remember this Young his name is Thomas Young. It's just the same guy. He established the interference theory. The certain genius. Okay, this Young's modulus, he is used to describe the deformation. We call it compress. We call it compress. We just press on it, right? We get this kind of the compression deformation, and this kind of deformation. Usually, we use the name the Young's modulus, but this kind of deformation is not the only one. We can do another different thing. We can do shear, right? We can do shear deformation for this kind on our materials. So another thing we did usually is the shear modulus. The shear modulus is, we call it, the shear modulus is usually happen on the lateral, and the Young's modulus is on the perpendicular. So this kind of shear modulus, it will also give us a modulus for this kind of shear motion, it gives us the shear modulus. And the shear modulus is also widely used for some soft materials. For our researchers, they are doing cells or gels, they would not compress it. Because once you compress, because for gels and the cells, it's some kind of liquid. And for liquid, it's hard to compress, but you can do a shear motion. So, for the cells and the gels, usually they use the shear modulus. And another thing for the solid, another researchers, they will use the called the bulk modulus. The bulk modulus, they would like to measure its volume change, not just the shear direction or the compress. Instead, they are study the volume change. So the shear modulus and the bulk modulus, if you understand, if you used to play the algebra game, they are just do some scale transformations. So we know we want to describe we want to describe the elasticity for isotropic materials. We only need two components. these two components can be Young's modulus and the Poisson ratio. It can also be shear modulus and bulk modulus. So of course, what's the relationship between these two is just the scale transformations. What's the relationship between the P sigma and, P theta and the xy? We know the x equals to P sine theta. Cosine theta. Y equals to P sine theta, right? You play this kind of scale transformation. Of course, for modulus nu transform to the G and K, we have the same mathematical games, right? So once you get your materials, you have different ways to study it. You can compress it. You get the Young's modulus and the nu, or you can do shear and the bulk. You get the G and the K, and they are described the same thing. Okay, so we're talking about this because we have some researchers, they are studying cells and gels, and their instruments, they give us the shear modulus, they give us G on that instruments, and then you want to compare this G with our modulus captured in the AFM. We have some mathematical games. Okay, so finally we establish our framework here. Now we want to study the mechanical properties. The holy grail is we want to get the elasticity. If luckily our materials is isotropic, we can reduce our task significantly to obtain two numbers. One is Young's modulus, another one is Poisson ratio. So our game now is to get the Young's modulus and the Poisson ratio using AFM on nanometer scale, right? That's the topic today. Okay, so it's clear, right? Not done. Okay, so that's the topic today. Okay, then how to do it? Maybe go to another slides. The other slides you can take a look on it. It's just all on this on my textbooks. Okay, so we have some scales to make you familiar with how it looks like. For cells and the gels, its modulus is around kilopascals. And for some plastics, for example, this kind of plastics, its modulus is around gigapascals. And for some hard materials like this stainless steel, it's around hundreds gigapascals. And that's kind of the scales we want to we are facing. So basically, AFM will tell us the modulus ranging from cells to steels. Okay, so it's just from kilopascals to 100 gigapascals. Okay, so that's. Let's take 10 minutes break and we go back to the AFM to study the modulus. And the modulus, we have many we have many ways to measure it. So the basic instrument to get the modulus, we measure it macro scale. How we get that? Usually is something like that. So we get for this one, we need to get the sigma, we need to get the epsilon. So usually in the macro scales, we measure the modulus. We will get it back to force over A equals to modulus times deformation divided by length. So usually we want to get the modulus. For example, I'm a pen maker. I need to know the modulus of these plastics. So usually I will make some samples. So I will make a column sample. The height of this column is about the height, I call it the length. And the area, the section area of this column is A. And it make of this plastics. So I want to get the modulus out. So this kind of machine, I will play it on a platform. And then I have a stylus. I have a stylus on top. And this stylus is connected to a scale. I can measure the force applied on this plate, on this stylus. And then I put a camera here. And this camera is just to monitor the length change. And then I apply force, and this camera told me the real-time length. So the length will be the y scale, and the force, and the x scale will be the force. I apply force, and the length will reduce, right? So it'll be something like this. So from this one, because my total length I know, so it divided by the initial length, and the force I divided by A, and I transfer this into L0 divided by minus L divided by L0, and this one I get the force minus A. I get a curve, something like this, right? So the slope of this curve will be what? Will be modulus, right? Quite simple. So the macro scale way to do the modulus mapping is easy. If you have a large stylus, you make your sample to be uniform in this column shape. Easy, right? Easy. So that's the macro scales, and many materials, manufacturers, many labs has this kind of machines, especially for those polymers groups. They have this kind of machine to study the modulus. So for AFM, how we do it? So the AFM, we know your samples, right? You cannot always make your samples to a certain shape, right? You have a 2D materials, it's triangle shapes. You cannot make it into this kind of column. Not practical. So for the AFM, that's my mount. That's my materials, various shapes, and I have a very thin AFM tips. I have very thin AFM tips, and then use these tips to compress my samples, and then I get the force, the deformation, blah, 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 blah. My holy grail is to get the modulus. My holy grail is to get the modulus. So how to do it? So we compare these two machines. So for this kind of AFM study, do we have a fixed A? No. Do we have a fixed height or fixed length? No. We cannot do a similar thing as this one. Of course, we have AFM probes, so we can apply a force. So this force, finally, I can control it. I use the force to apply. I use the AFM probe to apply force on my sample and measure the morphology change. So I can get the deformation. So this one may be also known, but the area and the length, no, I cannot get it. So basically, I cannot get area, I cannot get the length. So I cannot obtain sigma or epsilon. So basically, no, I cannot get the modulus here. That's the real world is always imperfect. So I accept it. So my task now is I obtain force, I get deformation. And then from this tool, I can get stiffness. Okay, with stiffness, at least I know something. The next one is, if I know stiffness, can I get the modulus? So basically in our AFM, we have two tasks. First, we get this measurement done. We can measure force, we can measure deformation, then we can get the stiffness. And the second, once we have the stiffness, how we can get the modulus? That's our task. So today our topic will be today we will describe our techniques in these two parts. One is to do the measurement. Second, do some calculation or do some mathematics. We want to get the modulus out. Okay, so we starting from this one. We have how to measure force, how to measure the deformation. Okay, so we give some review about the AFM, the atomic force microscope, how we measure how we get it done. So the atomic force microscope, basically we have a probe and we get in touch with our samples. And there is some force between the probe and the samples. Of course, last year we described this thing. So that basically is just the electric force, right? The atoms in the probes, it has each atoms has the electrons, it has the nucleus. The samples it made with the atoms, it has the electrons, it has the nucleus. The nucleus has the repulsion, electrons has the repulsion. So basically, the probes and the sample, there is some electric force between them. Okay, and of course we need to consider the quantum mechanics. So we need to introduce some Pauli reactions. Pauli repulsions, blah 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 things. But basically, it's electric force. So we have the probe, we have sample. There is some force between them, and we give it some business name. This business name is atomic force. Okay, so we know that how we can measure our morphologies. So we invent this technique. We have a surface and it has a certain morphologies. And we want to study, we want to get its morphologies, how we get it done. So if we have a probe, if our probe can always scan on this surface, I mean, it's always in touch with my sample. And then I drag my probe to scan the surface. Since the probe is always in touch with the sample, the distance between my tip and the sample is always the same. So the probe will follow the trajectory of my samples. So we get the tip movement trajectory. It should be equals to the morphology. So that's the way how we can get the morphology of the AFM. So we get a probe. We control the force between the probe and the sample. We hold them at a constant force. And then we scan the probe on the surface. So the probe will follow the trajectory up and down, up and down, up and down. We record the tip movement trajectory. It will be the morphology. So that's the AFM techniques, right? So that's the probe, that's the sample, that's the atomic force. So basically, I need to control the force at a scan at a constant value. So how to get the force? With this kind of probe, there's no way for me to measure the force. So I need to measure the force. How people measure the force before? They use a beam or they use scale, right? You go to the supermarket, you want to get 1 pound of beef. So you need to use some scale to get it done, right? So basically a scale is just a beam. So I put my probe on a beam. And then once I apply an atomic force on this probe, the beam will bend. And then I measure the bend of the of my beam. I would get the force on this tip. So that's the basic technique of our AFM. So basically, there is a force between tip and the sample. And then we transfer this force into the band of my beam. And in the AFM, we call this beam cantilever. We call this beam cantilever, okay? So we get the band of the beam out. So the next, how we get this band out? So this band in the AFM world, we call it deflection. We call it deflection. So how to get the deflection out? So my next is I use another beam to measure the bend or to measure the deflection. I introduce a laser. This laser shine on the backside of my AFM probe on this beam or on the cantilever. It will reflect the lasers to a certain way. And I place a photo detector there. Once this beam, this cantilever has a certain bend, it will reflect the lasers to another directions. And it changes the directions, it will change the locations on my detector. So basically, this detector is a position detector. This position detectors tell me how this laser reflection changes. So we measure this laser reflection change. We can tell how this cantilever is bent. We know the cantilever. We know how the cantilever bent. We know how large the force is applied on these samples. So basically, we use a laser reflection to measure the force. So that's the basic principle of the AFM measurement, right? Quite easy. So in this position detector, it's just a perpendicular scale, right? I'm sorry, it's a perpendicular scale. It should give us X and Y. That's the location, right? And in the AFM world, we know it calls vertical and lateral. Okay, so finally, I can write it down. So the force, it will change. It will cause the deflection change. The deflection will cause the vertical or lateral value change. So our AFM will measure the vertical and we will get the force from there. So our topic, the first task today is how we calculate force starting with the vertical value. Okay? So we describe our movement. We starting with the macro scale things, and then we mimic that macro scale techniques to get this AFM done. So basically, that's my sample. I place it on a plate. Sorry, it's not good. Wow. I get a stylus. I'm sorry, it's not good. So I use the blue pen. Sorry. I use the stylus on it and I can apply force. I can record this force. And there is a camera to record the height. Okay. So that's the macro scale way. So we apply force to compress my sample to get the Young's modulus out. So basically, AFM, we should do similar thing. That's my sample. That's my probe. And my probe, I'm sorry, it should have a cantilever. And it apply a certain force here. And then I get the force. So the force is applied on my sample. So first thing I need to do some Newton's law, the stuff. I want to measure the stiffness of the sample. So basically, the stiffness is the force on sample divided by the deformation. But my AFM, I describe my AFM is in different way, right? This probe, this probe sense some certain force. This force will change the deflection of my cantilever. So the force, I write it down here, is the force on tip, right? But for my stiffness study, I need to know the force applied on the sample. So we need to do some Newton's third equation here. I think these two are equals each other. Of course, consider the direction. I should apply a elective here, right? So I want to get the force on sample. I change it to the force on tip. Force on tip will change to the deflection of my beam. I'm sorry, the beam, the name now is cantilever. The deflection of the cantilever will cause the laser beam reflection change. and the laser beam reflection change will be measured using vertical and lateral. So basically, we get the vertical change. We want to get this force on sample, right? That's something we did on the macro scale instruments. So that's the first thing. We get the force out. So how? I don't know. I don't know how, but at least that's my directions. I need to get, so the first step is done by Newton, thanks to Newton. My second step is how I transfer force to deflection. I don't know, my task number one. How I transfer the deflection to the vertical change, I don't know, my task number two. Okay, so once I conquer these two tasks, I can get the force on sample with starting with the vertical. Okay, that's the first. So that's the force. The second thing is on the macro scale, I use a camera to monitor the height change. Of course, now I don't have a camera here. I don't have a camera to monitor the height change. So how I can get the deformation? That's my another task. So basically, I get this task one, task two, and the task three done. I can get the, I'm sorry. I can get my stiffness. So once I get the stiffness, my first step is done. And then I need some help with the physics to get the modulus from the stiffness. And now I don't know. So our task today has 4. 1, 2, 3, and then from stiffness to get the modulus. Okay, so let's go, let's start. So the first, I need to do the same movement with my macro scale materials. I need to compress my sample. So how I compress my samples on AFM? So the same thing. Probe, and I should combine my probe onto a certain machine. Of course, this certain machine now its name is the AFM. This probe, we mount it on a certain thing. This certain thing can move in the Z directions. Of course, we know the name of this machine is scanner. This scanner can move in the Z directions. Okay, so I get the scanner move in the Z directions, and this scanner can record its position. So basically, it can record the Z locations. And then we have another laser stuff. And the laser stuff, once the cantilever, once the probe sense a force, it will change the deflection of the cantilever. And the change of the deflection, and it will cause the laser, the reflection of the laser change. It will give you the change of the vertical and the lateral value. So basically, my AFM is to make the scanner move up and down and monitor vertical. That's it. So this kind of measurement, we call it force curve. And we move the probe, we move the scanner up and down. We record the vertical change at different positions. I'm sorry, different Z positions. At different Z positions. So after that, we can get a certain curve, something like that. the y-axis is the vertical value. The x-axis is the z position. That's my and the final results, we call it a force distance curve. Okay, so for this kind of curve, for our movement, we move the probe up and down. So we will make it a two phase. The first phase, we call it approach. The probe is moving down to contact with my sample. And the second step is moving up to drag the probe away from the surface. So we call it a two phase. First phase is approach, second phase is retract. And usually in the we mark it with different colors. Okay, so the blue color is the approach, the red color is the retract. So in the next slides, we use the same fashion. And the approach and the retract is the word used by Brooker. And the other companies, the other techniques, they may use different word. For example, some other machines, they use the extend to replacing the approach here. But you know, they are doing the same thing. Okay, so up, down and then up. We are using the blue and the red, or approach and the retract. Okay, and then when we approaching the surface, let's try to draw the scale. The x is z, the y is vertical. So at beginning, my probe does not sense any force, so my cantilever will not bend. So we make this as a 0 point. For example, we make this as a 0 point. So starting from the 0, so that's my sample. So I assume my probe is here. I'm sorry. I assume my sample is flat, okay? I assume my sample is flat. Something like that. I assume the initial distance, I'm sorry, no, I don't know what's the initial distance, I don't know, okay? So it does no harm to assume, for example, assume this is 100 nanometers. Assume this is 100 nanometers, okay? So I use my scanner to push the probe to approach into my surface. So since there's no force between my probe and the samples, so the vertical value should be constant 0, right? Assume there's some noise to make it like a real world. Okay, there's some noise. So when it reaches around 100 nanometers, there's maybe some interactions between the tip and the samples. We know the probe is made up with atoms. It has electrons, it has a nucleus. The samples is also nucleus and the electrons. When they are far away from each other, the main interaction is I attract is your electrons, and your nucleus attract my nucleus. So basically, in the long distance, we sense some attraction force. So when the probe is approaching to my surface, when it's very close to my sample, it will sense certain attraction force. So the probe will be what? it will be dragging down by this attraction force. And then this probe sense a dragging force, facing bottom, okay? Facing bottom. So the cantilever will bend bottom. So the vertical will be negative, right? It will be negative. So at the Saturn, the probe attracted by the sample and it will get a slap-in contact on the sample. So we call this a slap-in. So now the probe sense a certain attraction force. So for example, some negative value here. And this one is attraction force. Okay, then we know the atoms. The main reaction between two atoms is mainly repulsion. The repulsion usually has three origins. The electric repulsion between two nucleus, main component. Second, the two electrons, I should say electron clouds. The electron clouds, it should also have the repulsion caused by the charge, right? And the third, we have the Pauli repulsion force. We can, the two electrons, when it get closer to each other, the quantum effect will take place. So that's mainly the Pauli repulsion. So when the probe gets contact with the sample, it will have a repulsion force. So the repulsion force will push the probe against, but I have a scanner. I constantly push it down. So the force will start to sense a repulsion force, and this repulsion force will increase. When it goes back to this zero, we can tell the probe is something like that. It does not bend up, it does not bend down. The force is kind of zero. And then it continuously pushing down, so the probe will bend up, So the vertical value will increasing. We make it a practical word, so we need to add some noise, okay? So, and when we do the macro scale things, how we do it? We need to make some setup, right? We don't want to compress my samples continuously because I may damage my samples, right? So I need some setup. I need to set some certain maximum force I want to apply on this sample. I want to get the elastic deformation. I don't want to damage my sample. So I will set a certain maximum. Once it reaches the maximum, I will retract. That's what I did in the macro scale. So for the AFM, for the nanometer scale, I did the same thing. So I continuously approach until I reach a certain maximum force. I'm sorry, I make it somewhere here, okay? That's my maximum force. Of course, this one is set by you. You can apply any force you want. You can even damage your sample, doesn't matter, but that's the setup. So I set up this maximum force and then I need to retract. So this goes to the second phase. The phase 2 is the retract. So since my sample is elastic, I compress the sample and release the force. It will follow the same fashion. That's the elasticity. So the red curve should move the same direction as my sample. Okay? But and once I reach this same point, usually I did not find my probe, my curve follow the same way completely with my blue one. Usually I would get some curves, something like this one. And this one, we accept this kind of fashion. We will explain why it will happen later, okay? So it will goes down until it reach its limit. So at this time, the probe is something like this. It will sense some attraction force caused by the sample. It drag my probe. It cannot let it release from the samples. And we call this kind of force adhesion force. Once I reach the maximum adhesion force, the surface cannot drag the probe anymore. It will release the sample. It will release the probe. So the vertical value of the probe will suddenly change to 0. And then it get rid of the surface. That's the fully force curve looks like. Okay, it has two phases. One is the approach. The second one is the retract. It has some certain certain benchmarks. The first, I have a slap-in contact. I have a maximum force. I have an adhesion force. Okay, so that's basically the my force curve. So we want to get more detailed talk about this one. The first thing, contact point. I want to get the contact point because I want to know when the probe touched the surface. Because after the contact point, I think I am compressing my sample. I am causing the deformation. Okay, so the contact point is used to, after the contact point, I am doing the compression. I can calculate the deformation. So on this curve, which one is the contact point? Which one is the contact point? So my first candidate is this. My first candidate is this one, the slap-in contact. So that's quite just follow my intrinsic idea. That's my sample. That's my probe. When it senses attraction force, it drags the probe down to contact my sample. Absolutely, this one is a contact. But for this idea, for this candidate, it has a certain defect. It's when we're talking about deformation, we get this idea from the macro scales. We're talking about talking about deformation. I need to compress my sample, right? I need to compress my samples. So usually this deformation means the reduce or means the compression of my samples. But when we're looking about this slap-in contact, we are measuring vertical. It means we are measuring the force on tip. This one is negative, means it senses the attraction force by the sample. So the probe senses a negative force, it senses a attraction from the sample. So this force cannot compress my sample, right? The probe sends a forcing down. The compressing means my probe is compressed my sample. It will change the height of the samples. A lactive force cannot compress my sample. So here, it's not compression. Once the force be the positive, means the tip sends a positive force. It's facing up. The sample can be compressed. So basically, after this point, the vertical value changes to positive. The probe sensing a positive force. And after this, I can say it's a compression. So usually the contact point in the AFM, the region, we use this one. We call it the contact point, not the slap in. And the second, adhesive adhesion force. This adhesion force, why the radical does not follow the same shape as the blue curve? Why it does not form the same form? Because we need to talking about the origin of the adhesion force. The adhesion force, of course, it should have two components. The first is the tip sample interaction, right? The tip sample, it has some interactions. It sends some attractions between tip and the samples. So the tip sample interaction, that's one component of the adhesion force. So basically, from this one, if you are talking something with, if you are talking about the tip sample interactions, I assume my curve should be like this. So the blue curve should be like this, and the red curve should follow the same trajectory, right? That's the pure tip sample interactions. But the real force curve we get is something like that. So there should be another component. Another component usually is caused by the water. Okay, so let's talking about some chemistry. So here is my sample. And we know we are just using the, in the atmospheres, there's always water in the atmospheres. And this number is measured by the humidity, right? So basically, there is a certain water layer on my sample. And now I have a tip. And this tip is usually made up with the silicon or silicon nitride. On, on the surface of the silicon or silicon nitride, we know is always oxidized by our air. So usually is some hydrooxygen. So this hydrooxygen, basically it's hydrophilic, right? It's hydrophilic. And we are talking about the AFM probes. The AFM probes is what? It's kind of micrometer or nanometer scales, so it's quite small. So let's consider. Now we have a hydrophilic surface touching on my sample. And this one is quite small. So on this interface, we have a certain thing called surface tension, right? So the surface tension will drag the water come up on the surface of the sample. So the water will climbing up and it will form a meniscus on the probe. It has nothing to do with the hydrophilic, it has nothing to do with the sample. The sample can be hydrophilic, can be hydrophobic, doesn't matter, because there's always a water on the surface. The hydrophilic or hydrophobic of the surface will only change the contact angle here, right? If it is hydrophobic, it will be something like this. If it is hydrophilic, it will be something like this, right? It just changed the shape on the sample side. But my probe is hydrophilic, so it will always form this kind of concave meniscus. So on this concave meniscus, the direction of the surface tension will be here. So its perpendicular or its vertical components is here, right? So if I want to drag my probe away from the surface tension will drag my probe down. So this kind of surface tension will drag my probe down, will drag my probe against my scanner. So once I drag the probe on atop, the surface tension will drag my probe, and it will cause this kind of adhesion, right? So that's a region of the adhesion part. Okay, so that's the surface tension. But when we do the approaching step, when we're doing the approaching, the probe is approach to the samples. If the probe does not touch the surface, it will not form this kind of meniscus, right? So in the approaching region, there is no surface tension. Once it contact with the surface, this meniscus formed. So the surface tension caused the adhesion force will only be observed in the retract region, not in the approach region. So the approach region, we only observe the tip sample interaction. Basically, it's chemistry. But in the approach, the surface tension takes place. We observe surface tension. So our adhesion force observed in the retract region is much larger than this attraction force observed in the approaching region. That's the difference between these two. Okay, so there are some researchers, especially some there are some chemists, they want to study these interactions. So they will be focused on this one. So for example, there's some typical applications. We call it the single molecular force spectroscopy. For example, I'm a chemist. I want to study the interaction between gold and the thiol. Right? That's a quite famous chemistry. We know there is a certain interaction between the gold and the sulfur atoms, the gold and the thiol. So as a chemist, they want to measure the bond strength between the gold and the thiol. How we do it? How we measure it on the molecular way or on the nanometer scale way? We can do. We have a certain thiol surface. We have a gold probe, and we measure the interaction force between these two. So if we want to measure the force between these two, I can do a AFM to get it done. because I measure the interaction force, I can get it done. But as we said, the surface is covered by water. With water, our adhesion force will contain the surface tension. So usually we need to get rid of the surface tension's influence. The most to get rid of the surface tension, we usually have two methods. The first one, of course, get rid of the water. So we need to get it done in a dry material, in a dry atmospheres. And usually we need a glove box. Okay, but glove box, nobody likes it. I'm sorry, it's not a good atmosphere. So another way is we completely put our the setup in water. So if we sink our probe also in water, the meniscus will be gone, right? Because there is no air liquid interface. The complete thing will be sink in water. No matter how tip get in touch, will get away from the surface, there is no surface tension because there's no meniscus will be formed in this surroundings. So in this setup, the force we measured on this adhesion force here is purely tip sample interactions. So for the adhesion force, we know now it contains two parts. One is the interaction, another one is water. I'm sorry, another one is the surface tension caused by water. If you really want to measure something, I mean, if you really want to measure the tip sample interactions, we need to consider the get rid of the water. Use glove box or get it done in the fluid. Okay, so that's the chemistry. We have the fluid setup, right? Okay, doesn't matter. You give some the opportunity to book, okay? Uh, so let's continue. So okay, so finally we get the force distance curve down. So we can get the we can have the two details we need to discuss. First, this one here is my contact point. Here is the adhesion. The adhesion has two components. One is the interaction, one is the surface tension. Usually we hate the surface tension. Okay, so we get this curve down. We get this curve down, but remember the horizontal value is the Z position. The vertical the y-axis is the vertical. We really want is the force and the deformation. And from its slope, we can get the stiffness. That's our idea, right? Basically, that's our idea. So we have some way to go. So we need to how we change the vertical into force, how we change Z into deformation. Okay, maybe we just take 10 minutes break and go back to get it to get this stiff result. Okay, 10 minutes. So we have the force curves. We define the contact point. We define the adhesion force. So we try to get our force and the deformation out. So do the easiest thing first. So that's the deformation. So the AFM structure is kind of a beam. So this is my AFM probes, and I fixed it on a Z scanner. And I can record the Z scanner's positions. So this one can give out always give out the Z scanner positions. And then the probe will touch the surface. So on this side, so the Z scanner is moving down. So here is a delta Z. And then on these beam structures, so the probe will sense the force caused by the samples. So there's an interaction force between the probe and the sample. And then this force will cause the deformation. I'm sorry. Let me draw it. So the scanner is moving down. Let's assume it's moving down here. So here is the delta Z. And then the probe will be apply a force on this on the surface. So the probe, it will bend up. It will cause a deflection. At the same time, the force will cause the deformation of my sample. So the sample will be compressed. So it has two contributions. So here is the deformation I want. But at the same time, it will cause a over deflection. Since this is a beam, so we have a quite simple relationship is the deflection plus the deformation equals to the delta Z. So that's the way we can get the deformation out from the AFM. So delta Z is recorded by my scanner. So I have a Z scanner to move it up and down. I can get the delta Z. And the deformation is what I want. The next topic is the deflection. And the deflection, we have the same, we have our roadmap here, is the force on sample equals to the force on tip. That's the Newton's law. And the force on tip, it will go to the deflection. And the deflection is measured by my vertical value. So basically, our AFM record vertical, record delta Z, and we want to get force on sample and the deformation. So the whole idea is focused on how we can get the deflection out, right? The whole idea is how we get the deflection out. So basically, we need to know from the vertical goes to the deflection, right? That's the idea. Okay. So let's go to. Sorry. Here. Let's go to this idea, how we can get the deflection out from my vertical value. Okay. So the idea is to get from the vertical to the deflection. So actually we want to get some coefficient out in this step. This step, usually we call this coefficient deflection sensitivity. It has many names among different AFM makers. Some other AFMs, they call it different names, but it's just the same thing. We want to get the deflection out from the vertical. And we call this coefficient deflection sensitivity. And of course, its unit should be meter per voltage. Usually it's nanometer scale, so usually it is nanometer per voltage. Okay, so how we can get this out? We need to certain, that's the beam theory, and we will talk about later. But basically, we want to measure we want to get the deflection sensitivity out. So the way to get the deflection sensitivity out is we need to measure it. So the deflection, what's the relationship between the deflection? So for our force curve, we get a vertical change as the z. And we have another relationship that the deflection plus deformation equals to z. So that's our curve. That's our curve. So the red curve should be the similar. So I just show the blue curve on this slide. So we want to get the deflection over we want to get the deflection out. So our idea is if we have a certain sample, the deformation is 0. And then we can easily calculate the slope here on the force curve on this sample. We can get the deflection sensitivity. That's our basic idea. So the deformation equals to the 0 means the sample is infinite hard. So if we have a super hard samples, we can assume its deformation is almost 0. Of course, what's the sample? Usually, we need to get this standard sample out. In most applications, this sample is just a sci-fi. The sci-fi, the material sci-fi, we know it's the alpha aluminum oxide. It's alpha phase aluminum oxide. It's super hard. It's the modulus of these materials. It's about 700 gigapascals. It's super hard. So we can use this sci-fi as a standard sample. We compress on sci-fi. Since the stiffness or the modulus of the sample of the sci-fi is so large, the deformation we can assume is almost 0. And then the deformation is almost 0, then we can say the deflection is almost the same as the z. So that's our whole idea. So we do a force curve on this sci-fi sample. And on this sci-fi sample, from the slope, we can calculate the deflection sensitivity. That's the way we call it a deflection sensitivity calibration. And usually we need to get this sci-fi sample to do it. And this sci-fi is, of course, a standard sample used for this calibration. And some details we need to talk about. Is the sci-fi the only choice? No, because we said here is we only need the deformation to be 0. So if we have a hard probe, of course we have to use the sci-fi. That's the only choice. But if we have some certain soft probes, the probe itself is quite soft. For a soft probe, you use a glass, you use a silicon, you use a sci-fi. It's almost the same for them. So for certain soft probes, doesn't matter. So if we are doing some research on cell, gel, or some, hydrogel, something like that, the materials is almost kilopascals. The probe, of course, we should use some soft probes. So for this kind of thing, the sci-fi glass silicon is almost the same. So we don't need to always use sci-fi for them. Usually for cell and gel, we would just use glass. Glass slides will be good enough for them. Okay? Of course, for hard probes, we need to use sci-fi. Second, if we are using a quite dirty sci-fi, there are some oils, there are some the organic defects on this surface itself is not that hard. So we need to make sure our sci-fi is clean. We need to make sure our sci-fi is clean. So for this kind of clean, so in the chemistry, when we're talking about clean, it's not always easy. So we have many ways to clean our surface. The first choice, easiest way is to use plasma. Plasma is a quite good choice, easy to handle. Just put it in the plasma cleaner, say 30 seconds or 40 seconds. It can get rid of the oils, the organic defects, the organic contaminants. It's easy to do. Second, you can use some nowadays they have some gels to clean it, because this kind of clean is usually done in the semiconductor industry. We know for the semiconductor industry, we need our sample to be quite clean. So in the nowadays semiconductor industry, they use a certain glues or gels to clean our surface. It's just similar thing like a gel. It's a liquid, and you drop it on the surface, and after several minutes, it will be dried, and then you can peel it out, and it will form a gel, and this gel will get rid of the dirt on the surface. So that's a good way. That's the gel. That's the semiconductor gel. That's the semiconductor gels. And the third choice, you can use chemistry, right? The chemistry is so strong. You can use sulfuric acid. You can use hydrogen dioxide, those things. That's and in the chemistry, we have a certain solution we call the Perano solution. This Perano, you know, it's a certain fish in Amazon. It eats people. Okay, so it's 食人鱼. Okay, so this Perano solution is we have different components. The most common one is sulfuric acid plus hydrogen dioxide. It's so strong, it can eliminate everything. Okay, so it will just give you a clean surface. So this Perano solution, because it requires the sulfuric acid, and the sulfuric acid is so dangerous, so it's not that commonly used. So usually I would suggest plasma. Okay, and the plasma is easily found in our facility. You can use plasma. And if you have some semiconductor fab, you can choose this one. This gel is widely used in the semiconductor fab. You can use that. Also quite easy. And of course, if you are a chemist, the third one may be your choice. Okay? And the same thing will be applied to our other substrates. For example, you are doing some, you want to do some mechanical study on cells or gels. Usually you will use glass slides. And for glass slides, you can just use chemistry way. Okay, so that's the thing. And we need to emphasize here is on the sci-fi, after a long time, the water will suck the dirts, organic dirts, the organic dirts, the salt in the atmospheres. It will form a quite hard shells. I'm sorry, a quite hard shells on your surface, and this shell is quite strong. And so when when you want to calibrate with some quite hard probes, and these shells can be damaged by these hard probes, but it's not sci-fi. So for quite hard probes, especially the so-called R-TESPA 5 to 5, it's very hard to do the calibration because the water will form this kind of contamination shells on the surface. So if we want to calibrate this kind of hard probes, we may need to clean our sci-fi. But for other soft probes, you don't clean the sci-fi solidly, you can still get some good results. Okay, that's about the sci-fi calibration. Okay, so this step is quite easy. We can just get it done on the softwares. So basically, you get your sci-fi samples, place it on the AFMs, and then get a force curve on it, and the software can automatically calibrate the deflection sensitivity. Quite easy, but you need to give it a print. You need to get the sample preparation done. Okay. Now we need to talk something about this deflection sensitivity. For the AFM, we are just, this is our probe, this is our tip. It touches the sample, it sends a force, and then it will cause the band of our cantilever. It calls the band of the cantilever, and then this band of the cantilever is captured by the vertical value. So the deflection, usually the deflection is defined in such way. We have a probe, it has a band, and the Z displacement, we call it deflection. That's the so-called the ZC here means. And then we need to consider, okay, what's this ZC really means in our cantilever? Oh, sorry. So this is our sample. This is the cantilever, okay? So after a certain force, it will cause and here is the so-called ZC. That's the ZC. Okay, so this ZC is the so-called deflection. But what is our vertical measurement? The vertical is actually we have a probe. We have a laser to shine on our surface. And once the probe bend, we will cause a vertical change. So actually the vertical is proportional to the bend of the cantilever. So the vertical actually is an angle change. Or in the calculus, it's a slope change. So the vertical value we actually measured is the slope of the cantilever. So it should be dz versus dx. That's the slope of the cantilever. But the deflection we are talking about is just the z. So the relationship between the deflection and the slope, of course, is just times the length of our cantilever. So it means the longer my cantilever is, the dz versus dx will be smaller. So that means if we have a long probe, if we have a long cantilever, this deflection sensitivity will be less sensitive. We want to our measurement of the deflection. We should use a short probe, right? That's the idea here. That's the idea here. A short probe will give you a better deflection sensitivity. Okay, so that's the deflection sensitivity. So let's go back to our force measurement rod. We want to get the stiffness. We have the force, stiffness, and the deformation. This is our goal. So the force is force on sample equals to force on tip. And the force to tip will cause the deflection of my cantilever. And the deflection will be measured by vertical. So this one is Newton's law, third Newton's law. This one is done by deflection sensitivity. And my deformation. Deformation equals to z minus deflection. Deflection, nowadays I know the deflection is deflection sensitivity times vertical. So finally, Newton's law get this step down. Deflection sensitivity get this step down. Deformation, I get it down. So we have the last step is to establish the relationship between the force and the deflection. So this one in the AFM, we call it spring constant. That's the last one. So we have a probe, we have a cantilever, and this cantilever will have a deflection. So here is the force. So now we have the deflection. How we get the force? That's the so-called the last step. So when we look at this, we can say, okay, this is just a beam, and we bend the beam. We apply a force, we will bend the beam. So actually, we want to establish the force deflection. This coefficient here is just stiffness of my cantilever. So this coefficient, usually in our AFM community, we call it SC. We call it SC. And in some another in some other researchers, they consider, okay, this is just a Hooke's law, this is just a spring. So they will just use Hooke's law to write it down. Force equals to K times delta L. So they also use a K for this. So the K, usually the name is the spring constant. Or the SC is the stiffness of the cantilever. They are actually talking about the same thing. So in the different reference, you may say different description, but we are just talking about the same thing. KC or SC, they are the same thing. Okay, so the next topic is how to get the K out. This kind of spring constant calibration is a main main topic 20 years ago. People established many ways to do this kind of calibration. So nowadays it's already quite mature, so we can just choose a way for us to get it done. The first one is the so-called the dimensional models. I'm sorry, the dimensional models. Actually, we are talking about the structure mechanics. So our mechanical theories nowadays can establish we have a certain shape, we have a certain materials, we should be able to calculate the stiffness of this device. That's the mechanical theory, right? So actually we get the shape of our cantilever. We get the materials of the cantilever. That means we can get the modulus of our materials. We combine them together. We can calculate back the stiffness. That's the theory. So this kind of theories, it will ask you for many geometry things. What's the width? What's the length? What's the angle of our cantilever? And then from this geometry, we use the theory to calculate out the stiffness. That's the dimensional models. Dimensional models has been used widely, but nowadays we prefer not to get this done because it requires us to do the accurate measurement of the geometry of the probes. That's not very user-friendly, okay? So because if you want to do the geometry measurement, you need to do the SEM, and people hate to do SEM before AFM. So it's just a theoretical methods. Nowadays, people use quite widely. They call it. I'm sorry. Another method is the so-called static. Is the so-called static deflection measurement. This one is usually for the metrology. Oh no, I need to write this down. This kind of static deflection measurement is for metrology. Means if we can get if we have a calibration sample, and this sample is just a cantilever, the stiffness of the cantilever, I'm sorry, another stiffness, I'm sorry, if we have a standard cantilever and the stiffness of this cantilever has been already calibrated, and then we can use this one to calibrate our AFM probes. For example, let's use this way. Let's use this way. For example, we have a certain cantilever. We purchase this cantilever from Institute of Metrology. And the Institute of the Metrology, they will calibrate this probe, this cantilever first. And then it will tell you at this point, the stiffness of this beam is already known. And I write it down as the reference stiffness. And then I get my AFM probes. And I use the AFM probe to compress on this point. The black one is my AFM probes. The gold one is my reference. I compress on this point, and then I do a measurement. I do a full scale measurement. And then for this one, I need to get the KC. The Newton's law told me the F tip equals to the F sample. The F sample equals to the reference stiffness times deformation. The F tip equals to the KC times deflection. And the deformation, we already know delta Z minus deflection. The deflection we know is deflection sensitivity times vertical. So this one can be measured. This one can be measured. We calibrate this one. And the S reference, we purchase it. The Institute of Metrology will told us. So this one is already known. The deflection equals to the deflection sensitivity times vertical. So the left side is also known. Then the KC is out. That's the static deflection measurement, the how it's done. Okay, it looks like quite simple, but actually almost nobody use this method because this probe, I'm sorry, this cantilever, this reference cantilever is super expensive. Usually it's thousands dollars for this cantilever, so almost nobody to get this kind of cantilever done. So it's just for some extreme accuracy research. They need the measurement results to be traceable. They will consider this method. And I would say this method is not that easy to conduct in the experiment because they only calibrated the stiffness on this point. So we need to make sure our probe do the full scope on this point quite accurately. This experiment is not that easy. Okay, so that's another method. So Brooke has this kind of probe. Brooke has this kind of reference cantilever. It's something like this. It has 3 cantilevers. This 1, 2, 3. They are accurately calibrated, and this probe, I remember, this cantilever, I remember, is $3,000 or $4,000. It's super expensive. So another one is more user friendly. Is the so-called the Cleveland method. I think we can finish the spring constant calibration today. So the Cleveland method. it's there are some basic principle here we need to talk about. So for this thing, we need to do some the physical model studies. So let's talking about this one. We have a probe, we have a cantilever. We apply a force on it. And the force will cause the deflection of the cantilever. And then we call this direction Z. And then the deflection will be taken place on the Z directions. So we write down our equation. The force equals to the SC, or KC doesn't matter, times Z. And then if we, delta Z. And then we define the force 0, the Z equals to 0. So this delta Z can be write down as the 0 times the Z distance here. So the equation finally SC times Z. Quite easy, right? For the force, we have another way to describe is using the Newton's law. The force can be write down as its mass times its acceleration. dz equals this, right? So finally, we establish this kind of derivation equation. We solve this equation. Plus SC divided by M times Z equals to 0. And for this equation, it's easily solved. So its solution will be a certain value times cosine of frequency times t. That's our solution. And for this frequency, easily to calculate, omega 0 equals to SC divided by M square root. Right? Because you bring it into this derivative, the cosine will be negative cosine omega 0 t, and this one will be omega 0 square, right? It's easy to solve it out. And for this omega 0, we give it a name, a resonance frequency. Okay, a resonance frequency. So that means our resonance frequency is related to the mass of my cantilever and the spring constant of my cantilever. If I can measure the frequency, I may be able to get the spring constant. So we establish our equation. I write it down. Omega 0 equals to the SC divided by M. And the omega is the angular frequency, and the omega can be transferred into the frequency by divided by 2 pi, right? That's the angle. Okay, so people, one guy named Cleveland, he think about this method. If I can add another mass on the probe, then I may be able to obtain the spring constant of the probe. His method is usually for those one they need to glue some spheres on the probe. There are some researchers, they need to glue a sphere on the probe and then use the spherical probe to compress the samples. Usually some cells, some gels, they will do this. And this sphere, they can easily to calculate its mass by density and diameter. So they can do establish this way. So we have an original probe. We have original probes. And then on this original probe, I measure its resonance frequency. And I can get the resonance frequency F0. And then I can, from this original probe, I can establish this frequency. And then I glue my sphere on the probe. I do the resonance frequency measurement again. I can get a F1. And since it's the same cantilever, the spring constant K should not change. Then I have these two equations. I have M unknown, K unknown. So I have two equations, two unknown values. I can get the spring constant K out. Combine these two equations. And this one is the so-called the Cleveland method. Widely used for the glue spheres AFM probes. Quite smart. Okay. So the last one we want to talk about is the most frequent one is the thermal tune. For this thermal tune, its theory is kind of a little bit it requires some theoretical establishment, and so for a cantilever, I consider this cantilever. I place it in the atmospheres. I would say this cantilever is affected by the airs. The air molecules will just collide on this cantilever, and its Brownian motion will cause the probe to do a certain vibration. And then this vibration is caused by air molecules. So I would consider the vibration energy is provided by the Brownian motion of the air. And the Brownian motion of the air can be described by the thermodynamic. So basically, that's my assumption. The vibration energy equals to the thermodynamic energy provided by air. So the vibration energy, how I calculate it? Easily, force times distance. And the force, we have the Hooke's law. So SC J dz. And the integral of this one is easy, right? It's spring constant times J squared. And the thermodynamic energy, is we calculate the thermodynamic energy. The result is something like that. That's the for this one we need to go back to the thermodynamics, and the theory is there. and the results, we will jump this kind of part. It's a long way to explain this. So we assume we know this kind of results. The KB here is the Boltzmann constant. The Boltzmann constant is equals to the ideal L constant divided by the Avogadro constant. It's the 8.314 divided by Avogadro constant. Yeah. So the SC is what we want. The KB is a constant, easy to get. The temperature, easy to measure. So once we measure the temperature, we measure the Z. The Z actually is the deflection, and we know the SC. So the formula here is here. The formula here is here. So this so-called thermal tune is we just place the probe on our AFM machine, and we observe the deflection value against the time the probe is vibration. So we will say something like this. And from this curve, we get the amplitude out. The amplitude is the Z. We get the amplitude out. And then we get the amplitude out, we get the temperature, we can get the spring constant out. And this method, we call it thermal tune. Or in other AFM instruments, they call it the thermal noise. It's the same thing. Okay, so for this kind of method, it will be this method is optimized for some soft probes. Because for those hard probes, this deflection will be quite small. It will be quite hard to measure it. So usually it will be applied to some soft cantilevers. Okay, so for this one, we use it most widely in our lab. We use this kind of thermal tune. We get the temperature out, and then we get the spring constant out. And we have another method, we call it the SAID method, but it requires some hydrodynamic explanation, so we may save it for tomorrow. So finally, we get the spring constant out, and we will get it done in our roadmap. That's the SC. So basically, we're starting from the vertical values. After calibration of the deflection sensitivity, we know the deflection. And then we know the deflection, we finish the calibration of the spring constant, we will know the force. And the Newton's law will give us the force on the sample. On the other side, we need to know the deformation of the sample. The deformation of the sample, we can use the delta Z minus the deflection. And the deflection is here. So after the calibration of the spring constant and the deflection sensitivity, we definitely will know force, we will know deformation, and then we get the stiffness out. That's our AFM measurement theory. Okay, so tomorrow we will finish the last part. From the stiffness, how we can get the modulus. How we can get the modulus. Okay. Sorry, we will stop here, and tomorrow we will finish the SAID method, and then we establish this step. And then we finish the force curve, and we can go to our peak force QM techniques tomorrow. Okay, so I think today is all. Thank you so much.